In the last lecture, we considered a quantity Q, whose dimension is a function of only one dimension. Say, for example, length. We asked what's the functional form of f on L, and we showed that it should be a power law, for example, L to the power alpha. We may ask if dimension of Q depends on more dimensions. For example, it may depend on length, time, mass, or other dimensions, and ask what's the functional form of f on these dimensions. Let's consider two definitions. The dimension di's are dimensionally independent, provided that we have k independent dimensions. We define independent dimensions by this relation. The multiplication of all these dimensions to the powers alpha 1, alpha 2 until alpha k is equal to 1, provided that all alpha i's are 0. If this holds true, then we call that d1, d2 until dk are dimensionally independent. And second definition is power law monomials of quantities xi. It's defined as x1 to the power alpha 1 until xk to the power alpha k. This is a power law monomial of quantities xi. Now, let's return to our first question. What's the dimension of a quantity, which depends on several dimensions? With this exactly similar reasoning as the previous lecture, we can show that this should be as L, for example, to the power alpha 1, T to the power alpha 2, M2 to the power alpha 3, and etc. Then the dimension of any quantity in physics is a power law monomial of independent dimensions. Sometimes we talk about fundamental or independent dimensions. For example, in mechanics, usually we choose L, length, time, and mass as independent dimensions, and express other quantities in terms of these dimensions. However, we have freedom in choosing the independent ones. For example, if we choose the class length, time, mass in mechanics, other quantities can be expressed, the dimension of quantities can be expressed in terms of these. For example, the dimension of velocity is L t inverse. The dimension of L and T are independent, but the dimension of V is not independent. Its dimension is dependent on length and T. It can be written as LT inverse. But the dimension of L, T, and V are dependent with our definition here. L T inverse V inverse is equal to 1. We have alpha 1 equal to 1, alpha 2 equal to minus 1, alpha 3 equal to minus 1, which all of them are different from 0. But L, T, alpha 1, alpha 2 is dimensionless provided that alpha 1 and alpha 2 is equal to 0. Okay, we can choose other class of independent dimensions. We can choose, instead of L, T, and M, the class of, then T has dependent dimensions. The dimension of T is LU inverse. So, our first job in dimensional analysis is choosing class of independent dimensions. In mechanics, usually we choose LTM as independent dimensions, but we can choose other classes. For example, or where R is dimension of density, or if we show dimension of force by F, we can choose the class of dimensions as F, U, and R. So first we choose our class of independent dimensions and express the other quantities in terms of these independent dimensions. Now let's consider the Buckingham's Pi theorem. Any equation containing physical observables. We have considered that there are Q1 until Qn quantities, n quantities. Qi, where I is 1, 2 until n. These quantities have different dimensions. Some of them are dimensionless, some of them have independent dimensions, and some dependent dimensions. Let's consider we order the quantities with independent dimensions as Q1, Q2, Qk, whose dimensions are independent. The remaining quantities are dimensionless or have dependent dimensions. For example, the dimension of Qk plus 1 can be written in terms of power law monomials of d1, d2 until dk. If we change the system of units, for example, changing meter to centimeter, numerical values of quantities Q1, Q2, and Qk scales by some factors, for example, B1, B2, and Bk. This is due to a changing system of units. Then all quantities which have dependent dimensions are also changed. For example, Qi, I equal to k plus 1 until n, change to which depends on their dimensions. For example, Qk plus 1 changes to B1 to the alpha I1, B2 to the power alpha I2, Bk to the power alpha Ik, Qi, where I is equal to k plus 1 until n. Then the equation, the physical equation, changes to where no, we can choose B1 equal to Q1 inverse, B2 equal to Q2 inverse. We define these as pi, where, for example, any of these pi's are the ratio of quantities with dependent dimensions over power law monomials of quantities with independent dimensions. It can be easily shown that all these pi's are dimensionless. Let's consider, for example, pk plus 1. pk plus 1 is qk plus 1 as dimension is the dimension of pi 1 is the dimension of qk plus 1 or dimension of q1 to the power alpha k plus 1 k2 to the power substituting these, we can easily see that pi k plus 1 is dimensionless.